right, guys. Today we're going to be talking about matrix chain multiplication. It's a fun problem, and we have a dynamic programming algorithm for this, okay? So what's a matrix chain multiplication problem, or just a matrix chain problem? We're given n matrices, A1 through AN, of dimensions R1, C1, R2, C2, rows, columns, etc., all the way up till n, right? Now, if we have to be able to multiply these matrices, of course, we are given that Cj is equal to Rj plus 1 for all the neighboring matrices. This is because that's how the matrix multiplication is defined. So if, for example, we have a 10 by 20 matrix, we can multiply it with a 20 by 5 matrix or a 20 by 7 matrix, etc., etc. And the 20 by 5 matrix itself, we can multiply with 5 by 7 matrix, 5 by 10 matrix, etc. So the number of columns in a matrix must be equal to the number of rows in the next matrix. So, but you cannot multiply a 10 by 20 matrix with another 10 by 20 matrix. So this is just sort of the backgrounds of the matrix multiplication. So we're given these n matrices, and we have to compute the final matrix product A1 through AN. This is an associative operation. That means we can multiply in many different ways. We can multiply A1, A2 first, or we can multiply A2, A3 first. We cannot shuffle the sequence. We have to keep the sequence as it is, but we can combine any two matrices in whichever order we want. So that's really the problem. In what order should we multiply it so that it takes the minimum number of computations? And the number of computations differ. That's the first observation we will make. Now, when you are multiplying two matrices, let's suppose they're of size A, B, and BC. So B again has to be the common, the number of columns and the number of rows in the next one. When we multiply these two matrices, the cost is ABC, and we will review that very shortly as well. So that's the matrix chain problem. So let's again refresh a little bit about how do we multiply two matrices. So when we are multiplying matrices, let's suppose we are given A times B and B times C matrix here. Finally, we'll have an A times C matrix here. For example, here we have a 2 by 3 and a 3 by 2 matrix. When we're done multiplying, we'll have a 2 by 2 matrix here. And how do we multiply it? Well, we take the ith row, in this case, the first row, the second column, and that gives us the first row and the second column of the final output. Similarly, take the first row, first column, get this element, etc. And what do we do is we take the dot product. So let's suppose we take this example, 5, 1, 7, and 1, 0, 3. We multiply 5 with 1, 1 with 0, and 7 with 3. Add all three of those up, and you get 26. And of course, if it's negative, you handle the math just like that. So it's 5 times 1, 1 times 0, plus 7 times 3 equals 26. That's the element that goes here. And that also, again, serves as a good reminder why the number of columns must be equal to the number of rows. So we can do the dot product here. So this is just multiplying two matrices. And as you can see, you have to produce A times C output entries. And it takes order B time, if this was an A by B matrix, to produce each value. So that's why we call ABC or R1, C1, C2 that it takes when we multiply these two matrices. Now, this is nothing that we're trying to optimize. This we just take as a given. Then when we are multiplying two matrices, this is just how long it takes. So we just accept this as it is. Now let's take a different example where we have three matrices, and these matrices are multipliable. So we have 3 by 5, 5 by 7, 7 by 2. But this time we take this parenthesization into consideration and say, okay, we can choose two different orders. One order is A1, A2 multiplied by A3, or A1 multiplied by A2, A3. Either way, you will have the same exact matrix as the final answer, which is going to be a 3 by 2 matrix, but the overall time is going to be different. So let's take a closer look at this point here. Let's suppose you multiply A1 times A2. That's going to be 3, 5, 7, this much time. Finally, you'll have a 3 by 7 matrix. You'll multiply that with A3. it'll take 372, and you've done 2 multiplications, add those up, so you get 147 units of time, operations or units of time. Similarly, if you do A2, A3, that'll take 572 time, and then we'll multiply that, a 3 by 5 matrix with a 5 by 2 matrix. It'll take an overall 100 units of time. So you can see you're almost saving 50% of the computation time, even though the calculations returns the same result, if we just know what's the right sequence, right order to multiply these in, okay? Now, how will we solve this? We'll solve this using our dynamic programming approach. So first thing we come up with is a notation. The notation is that we will be using is that let Mij denote the cost of multiplying matrices Ai through Aj. And it's measured again in these number of computations of the time units that we've been using. That's the notation we will say. We make an observation that Mii just means that we don't have to multiply any matrices. So that means we can just initialize or think of it as 0. M1n is what we were originally asked to minimize, to optimize here. And the question was, what's the sequence we should multiply in? So if you recall our introductory video on dynamic programming, there's a video link somewhere. If you look at our introductory video on the dynamic programming, the notation step says that we must come up with a notation that satisfies 2 key properties. That the first key property is that notation should be general enough that it can handle any sequence, any solution, as well as any sub-solution. And we notice that this very nicely, this notation, Mij, does handle every notation and every sub-notation. The second key property that we mentioned in that notation step in our introductory video is to say that even though the question might be posed to you as what is the sequence you're trying to find, what is the path whatever it is that you're trying to find, leave that aside for a moment and think about the quantity that you're trying to optimize. And here we see that the quantity that we're trying to optimize is the cost of multiplying these 2 matrices, and that's Mij. So this notation really handles both of those 2 considerations that we gave there. So this is the notation we will try to use here. We show that the principle of optimality really holds here. And this is sort of on a very similar lines as we have used in the past for the distance problem. But let's look through this way here, that if every way of multiplying a sequence of matrices can essentially be represented as a binary tree, the left half being the one operation, the right half being the other operation, then you multiply finally those 2 matrices, and we say that's our optimal sequence. Now, if the optimal sequence is given to us, then we are sure that the left-hand side and the right-hand side must also be optimal subsequences for the subproblems. That's what the principle of optimality states. And to prove that, we can prove that using a proof by contradiction, that if, for example, there was a strictly better sequence available in the left-hand side or the right-hand side, that would contradict a better tree overall, a better result, or a better solution overall. So given that the solution that was given to us was optimal, the sub-solutions must also have been the optimal solutions for the sub-problems. So that's how we can argue that the principle of optimality holds, prove it using the proof by contradiction here. So let's go to a recursive formulation here. So using this particular notation, we say that Mij is the cost of multiplying, again using the same example, the same notation as we are using in the proof by contradiction, the tree, the left-hand side, the right-hand side, multiplying 2 matrices that emerge from those 2, left tree and the right subtree. So we would just call it like cost of the left subtree plus the cost of the right subtree plus the cost of multiplying those 2 matrices, which can be recursively written as Mik plus Mk plus 1j plus the cost of multiplying those 2 matrices, which is simply Ri, Ck, Cj. Okay. Now, we do not know where exactly should we break this tree, how many matrices should be on the left-hand side and the right-hand side, and that's perfectly fine. We can simply condition over k to find the best, that's the minimum value of k, of the one that minimizes the value mij. So we would write mij is equal to minimum of mik plus mk plus 1j plus rick for the values of k between I and j minus 1. So that's our recursive solution. Once we have this recursive solution, we see that the algorithm is relatively easy to find. We just have to come up with the sequence here that we initialize mii to 0. We initialize mii plus 1 also to be a base case in which you're only multiplying those two matrices. That's simply equal to rici plus 1. Like we talked, that's nothing we're trying to we're not trying to optimize that. That just we take as a given, and then we simply build up our solution from the bottom up traversal by running in these two for loops for I is equal to 1 to n, for j is equal to 2 to n minus I, mii plus 1 is equal to minimum over k, etc. Now to see the time complexity of this, the time complexity of this algorithm is clearly order n cube. There are two loops nested within each other. And the third one, even though it's written as a minimum, of course, that's a loop as well. So it takes order n cube here, order n cube time here, where n is the number of matrices given. So this algorithm simplifies the sequence. It's nothing to, we don't want to be confused with the actual matrix multiplication problem. And that will take whatever time it takes. Here, we're simply trying to find the sequence that's going to be the right sequence here. And you might notice that there's a line here in the loop that says SII plus 1 is equal to arg min k. That's the line in which we are storing what is the sequence itself. Mi are just the cost values, but in the S values, we can store where exactly should we break our chain here. So if we have to multiply from 1 through 40, we'd say, well, then you have to go through from 1 to 11, 12 to 40, and then multiply those two. That's essentially what that S value is writing. So that's essentially the summary of your matrix chain multiplication problem. When you have to multiply n matrices, use the dynamic programming to identify the correct sequence. Using the optimal sequence can save you a very significant amount of time. That's what this algorithm does. It's a very good algorithm. Now, why are you multiplying matrices in the first place? Well, for many reasons. You could be doing something with image processing. You could be doing something with either in the neural nets, which all of these kind of problems, you heavily use matrix multiplication. Now, the number n could be large, but it's not generally not in millions. It's maybe about 100, maybe 300, whatever number, somewhere along those lines. 50 perfectly common too. So that's what you're trying to do here, is to multiply those 50 matrices, and the algorithm that we've just discussed will tell you which sequence to do the thing in, because ultimately you're trying to save power, save time in the overall operation here. If you want to learn a little bit more on this problem, there are faster algorithms available as well, even though for 50 n cube and even n may not be, for 50 or 100 n cube is really not that large on any reasonable processor, but still every little bit saves. So there are faster optimal algorithms. In fact, order n log n is very possible too. And an approximation algorithm is also known, which runs at order n time. Now, approximation algorithm, it guarantees about 85% of the best known. Now, that may not be worth it if the matrices are very large, but still that solution is also available. In fact, both of these algorithms are attributable to a famous researcher in this field, which is Te-Chiang Hu. He's one of the, he was one of the founding members of computer science at San Diego. So, and if you want to consider a generalization of this problem, and the generalization, because matrix multiplication is an associative problem, essentially we can make one generalization that if you have a given linear sequence of objects and you're given some binary operation, what is the way to compute the cost of performing that operation on any two objects? Just find the minimum cost to group the objects to apply the operation over the sequence here. Just like we're doing here, given n matrices, and we know how to multiply two matrices, but we're coming with a sequence to combine. So that's basically all I have for you. That's matrix chain multiplication, of fun dynamic programming algorithm. So have fun and keep learning.